Today is our lecture number 17. Today we discuss some theorems about differentiation, and before starting these theorems, first we will solve some questions from our exercise 2.3. So we start our exercise. Today first I would like to solve question number 10 from your exercise 2.3. The question is under root 1 plus x divided by under root 1 minus x. So this is your f of x, and 1 plus x divided by 1 minus x, or you may write this function is like, instead of writing this under root, you can write its power 1 by 2, and you can apply derivation. Now when we apply derivation, d by dx of f of x, or we also write it like dy by dx, because y is a function of this f of x, and f of x is equals to this function, this given function. So dy by dx is equals to d by dx of what? This function 1 plus x power 1 by 2 divided by 1 minus x power 1 by 2. And as the question is showing, it's a quotient rule we have to apply here. So what is the quotient rule? We take power 2 of denominator function, whatever the power in your function at your function, but you have to keep this thing in your mind. Whenever you apply the quotient rule, you have to give power 2 of this denominator's function, and then according to the formula, the denominator function will remain same over here, and then first we apply derivation on numerator function 1 plus x power 1 by 2. Minus sign is according to the formula. Then the numerator function will remain same, and we apply the derivative on this denominator function. Now we solve it. 1 minus x power 1 by 2, and then first we bring this power over here as a multiple of this factor 1 plus x power 1 by 2 minus 1. This minus 1 is according to the derivation rule, and then what we will do, we apply the derivation to the inner side of this power. Whatever you have a factor, first you will if you have a power on your factor, first you will solve the portion of a power according to the formula. We have taken this power over here as a multiple of this power, and whatever the power is, we will minus 1 from the original power. Then we when we solve the case of this power, we apply derivative on inside the factor. So here the same we have done, we applied this derivation to inside of our function. Again minus sign according to formula, then 1 plus x power 1 by 2. Similarly, again 1 by 2, we will solve the power 1 minus x power 1 by 2 minus 1, and then we apply the derivation on inside the function. So what is the function? What is then d by dx of what? 1 minus x power 1 by 2, and the denominator is same 1 minus x, and 2, and this 2 will be cancelled with this 2, and we have just 1 minus x. Again if we further simplify this equation, what we get? 1 by 2, then 1 by 2 1 plus x power minus 1 by 2, and then here we have two terms, and we apply this derivation separately. D by dx of 1 plus d by dx of this x, and minus 1 plus x power 1 by 2 into 1 by 2, 1 minus x power minus 1 by 2. 1 power x minus 1 by 2. And again we apply, here we have two terms, so we apply, uh, here we don't have this power, sorry, I have written this power over here, no need to write, because here when we solve the power we just differentiate the inner function. So d by dx of first 1 and then minus and d by dx of this x, and denominator is 1 minus x, 1 minus x. So here we have 1 minus x divided by 2 into 1 plus x, then 0 plus x minus 1 plus x, 1 plus x under root divided by 2 1 minus x, and here we have 0 minus 1, sorry, here we have 1, derivation of x is 1, so 1 minus x, and whole divided by 1 minus x, and when you simplify it more, 1 minus x under root 2 into 1 plus x minus 1 plus x divided by minus plus, this minus will be multiplied with this minus and you get plus, and 2 under root 1 minus x, and whole divided by 1 minus x. Okay, now if we take LCM, so what we will get, 1 2 under root 1 plus x, 1 minus x, then 1 minus x under root into 1 minus x plus 1 plus x and 1 plus x, and whole divided by 1 minus x, and under root and under root, 2 times under root, we get 1 minus x power 1 by 2 plus 1 by 2 plus under root 1 plus x 1 by 2 plus 1 by 2 divided by 2 into 1 plus x into 1 minus x under root, whole divided by 1 minus x. Then 1 minus x power 2 by 4 means 1 by 2, and plus 1 plus x 1 by 2. Sorry, 2 by 2 means 2 by 2, and 2 by 2 means we have 1 power. We take the LCM, 1 by 2 plus 1 by 2, so we get 2, 1 plus 1 means 2 by 2, 1. So here we have 1, 1, and then 2 into 1 plus x, 1 minus x, and whole divided by 1 minus x. And then if you 1 minus x plus 1 plus x divided by 2 into under root 1 plus x under root 1 minus x 1 minus x. We simplified whole this part, and then this x is cancelled with this. We have 2 2 by 2, 1 plus x power 1 by 2, and 1 minus x power 1 by 2 plus 1. So 2 and 2 are cancelled. 1 divided by 1 plus x into 1 minus x power 3 by 2. And this is the answer of our question. And this question is also, you can simplify this question like I have taken this question like separately. You can, this is the second method through which you can solve this equation. Like if we have as we have under root 1 plus x divided by 1 minus x under root. I have taken in the question, the solution which I have given you, we I have taken the power separately. You can combine them like this: 1 plus x divided by 1 minus x and 1 plus x divided by 1 minus x power whole 1 by 2. So here first you solve the power, when you apply the derivation, now dy by dx, and when you apply power over here you take this power 1 plus x divided by 1 minus x, 1 by 2 minus 1, and then you can apply the power on just this inside the function. Now on this function you can apply the derivation, and the rule which you will apply here, that is quotient rule, same but without powers. So this is the second method. You can, it's up to you if you want to use this one and this one. So sometimes one question can be solved by using two three methods. So there is no problem. It's up to you which method you want to adopt. Okay, now next question. The next question which I will solve for you, that is question number 14. Question number 14. So here I have 1 plus x minus 1 minus x whole divided by 1 plus x plus 1 minus x. So solution is, this is our function y. This whole function is our y function. So first 1 plus x minus 1 minus x divided by 1 plus x plus 1 minus x. Before starting or differentiation, first I would like to simplify my this equation. So for simplification I would like to apply rationalization. So when I apply the rationalization, so what I will do, I will multiply and divide 1 plus x, this denominator, multiply and divide by rationalization. Okay. So when I rationalize this, when I simplify this whole part, I will get 1 minus under root 1 minus x square divided by x. After simplification of this equation, I will get this equation. So it's up to you. You will solve this equation and simplified it, and finally you will get this equation. Now you can apply the differentiation on this equation. So here we have y is equals to this, and dy by dx will become equals to d by dx of 1 minus x square, x square power 1 by 2 divided by x, and you have to apply just a quotient rule on this equation. And now this question is now very simple question, and you can solve it very easily. Now question number 17, in which you have to, the equation is given and you have to uh, prove some function. The question is, if y is equals to x4 plus 2x square plus 2, and you have to prove that dy by dx is 4x under root y minus 1. So it's a simple question, just differentiate this equation. So d by dx of x4 plus 2x square plus 2. You can apply this derivation on all the terms. D by dx of x4 plus 2 d by dx of x square plus d by dx of this 2. Now, according to the power rule, 4 into x, 4 minus 1 plus 2. 2 is this one 2, and when this power will bring here, we have 2 multiplied by 2, x power 2 minus 1 plus 2 into the derivation of a constant function is 0. So here we have 4x cube plus 4x plus 0. And then if we take 4x common, we have x square plus 1. And again, if we 4x into x square plus 1 square under root, there is no effect on the inner side of this factor. We have taken square and under root both at the same time, because 2 will be cancelled with this under root and the remaining equation will be the same. There is no effect of these two applications. Now I'm doing this because we have to prove, our question is, we have this function and we have this function and we have to prove this type of equation. Means we have to prove that this dy by dx is equals to 4x under root y minus 1. So this is what I am going to prove. So for this I have taken this power 2 and under root both on this equation. Okay, now the next step is 4x into, I'm going to apply this power on this factor. Simply this second formula of the formula of square, x4 plus 1 square plus 2 x square into 1, a plus b, a square b square plus 2ab. I've applied this formula. So 4x into x4 plus 1 plus 2x square. Okay, now 4x. If I x4 plus 1 plus 2x square, if I plus and minus this 1, again there is no effect of plus 1 or plus minus because both will be cancelled, and there is no effect on your original equation. Now equal to 4x, again x4 plus 2x square plus 2 minus 1. I have added these two terms, plus 1 and plus 1, plus 2 minus 1 is 4x. Why I am doing all this? Because here I need I will write the question over here. We have in our question y is equals to x4 plus 2x square plus 2. And we have to prove that dy by dx is equals to 4x under root y minus 1. Y means, here we have a y, means here we have to put this value x4 plus 2x square plus 2. And this equation I have derived here, x4 plus 2x square plus 2. So instead of writing this, if I write y minus 1, and this is what which I'm going to prove. So here we have dy by dx. So now dy by dx is equal to 4x under root 4 minus 1. So I have proved this equation. So this is the end of our exercise 2.3. Now there are some important theorems which is very important, and I will solve few theorems for you, and the rest of cases you can solve very easily. Okay. Now theorem number 1. Theorems. Now first theorem is derivation of constant. Prove that the derivation of a constant function is 0. Prove that derivation of constant function is 0. So how we prove? D by dx of c is equals to 0. This is the statement of our theorem, and the proof is, I will prove this theorem by using ab initio method first, which is also known as first principle method. So let y is equals to c. Here we have the function c. This is all, and you must keep in your mind, whenever we apply the ab initio method, we must remember the four rules, which are the part of our this method, and the same steps I will apply here. Now y is equal, the first step is y is equals to c. Y is equals to our function. Well, then this is the step 1. Now step 2. What is the step 2? We take some increment in y as well as in increment in x. So here we don't have x, so simply I write this c. So this is our second equation. And the next step, we subtract our second equation from equation number 1. So we subtract equation 2 from 1. So y plus del y minus y is equals to c minus c. So this will be cancelled, this, and simply we have del y is equals to 0. And the third step is, step 3 is, step 3 is we divide del y with del x is equals to 0. And step 4, we take limit. So when we take limit del x approaches to 0, del y by del x is equals to 0, means we have dy by dx is equals to 0. So whenever we have a function as a constant, what we do, we solve it by ab initio method, by definition method, we get 0 result. So this is our first theorem. Now second theorem. Now the second theorem is, prove that d by dx of c f of x is equals to c prime of x. Prime of x, d by dx of any function can be written as f prime of x. Both have same meaning. So when we apply, when we start, it proves the first step. What we will take, y is equals to c f of x. This is our function. and this is step 1. Then step 2, y plus del y is equals to c f of x plus del x, increase in y as well as in x. So this is first equation and this is your second equation. And same, second minus 1, we get del y is equals to c f of x plus del x minus c f of x. And if I take c as a common, so c f of x plus del x minus f of x. And the third step is we take step 3, we divide del x on both sides. So c divided by del x f of x plus del x minus f of x. Or we may write it c f of x plus del x minus f of x whole divided by this del x. Now step 4, we take limit del x approaches to 0, del y by del x, limit del x approaches to 0. We take c here because it's a constant, and we just apply this limit on this function f of x plus del x minus f of x whole divided by del x. And if you recall the definition of a derivative, you will see that this whole function is known as f prime of x. So this is the proof for our second function, second theorem. Now the power rule. The third is power rule. Power rule. In power rule, we have to prove that d by dx of xn is equals to nxn minus 1. You can apply this theorem, you can solve very easily. Same by ab initio method, you can solve this theorem. It's both part. I'm not doing this because in the start of our previous lecture I have done this type of question for positive for the rational number as well as for the for non-rational numbers. I have solved this. So you can see by using the same method you can solve this theorem very easily. And if you have any problem, you can contact me on my WhatsApp number. Now the fourth one is sum rule. Sum rule. In sum rule, we have to prove that the statement is f of x plus g of x is equals to f prime of x plus g prime of x. So when we start our proof, similarly, our first function is y is equals, first step is f of x plus g of x. Second step is y plus del y is equals to f of x plus del x plus g of x plus del x. Simply increase in y and increase in x as well. Now the same step, if this is our equation number 1 and this is our equation number 2, we subtract our second equation from first equation and we get y is equals to f of x plus del x minus f of x plus g of x plus del x minus g of x. And then our third step, what is the third step? We divide del x on both sides. dy by del x is equals to f of x plus del x minus f of x plus g of x plus del x minus g of x whole divided by this del x. And if we separate our equations, f of x plus del x minus f of x divided by del x plus, because the denominator is same, so we can use it on both denominators, minus g of x divided by del x. Now if we apply the limit on both sides, limit, the last step, limit del x approaches to 0, del y by del x sorry, del x is equals to limit del x approaches to 0, f of x plus del x minus f of x divided by del x, and this is the property of limit. Then we can apply limit on all the terms on which limit is applied. So x plus del x minus g of x divided by del x, and according to our definition this will become f of x, and this whole term become g prime of x, and this whole term is equals to f prime of x. So we have proved this theorem also, and by using the same step, same method, you can apply, you can prove the this difference rule. Now the very important, that is the derivation of product, derivation of derivation of product rule, sorry, derivation of product rule, product rule. In product rule we have d by dx of f of x into g of x is equals to its formula. The formula is f prime of x, means derivative of first function, second same, plus derivation first function same and derivation of second function. This is the formula, and we have to prove this formula. Same step, y is equals to f of x into g of x. This is your f of x. And the second step, increase in y as well as increase in x, x plus del x. And the next same step is what? We subtract equation 2 from 1. This is your second equation and this is your first equation. So we get del y is equals to f of okay, f of x plus del x into g of x plus del x minus f of x into g of x. Okay, now if we say that this f of x plus g of x is we move to next page. Okay, now in the start of this question we have this product rule, and here we have since we have y is equals to f of x into g of x, and if we suppose that let phi of x, instead of y, if I write phi of x is equals to f of x g of x, then our equation will becomes equals to phi x plus del x minus phi of x is equals to f of x plus del x g of x plus del x minus f of x g of x. What I have done? Okay. You can see here I have taken y is equals to f of x into g of x, and when I take the increment y plus del y is equals to f of x, this is the same case, and this is also the same thing happened here. Just if I will go back to here, and I will take instead of y, if I normally we are doing these same steps, but in product case, if I change my my supposition, instead of y, if I take phi of x, then what will be happen with these rest of equations? Actually, no, I'm taking the other supposition for the convenience of our calculation. Otherwise, this is okay if you want to take the same thing, same suppositions. Now I have taken y is equals to f of x plus g of x. That was the original function. And if I suppose that phi of x is equals to f of x into g of x, and when I subtract the both equation, what will happen? This thing will be happen. This thing. Because when I take the increment here, I will get x plus del x and same f of x plus del x and then g into x plus del x. And now this is your second equation and this is your first equation. And when you subtract from second equation to first equation, you will get this type of equation. Now, the next is we subtract and add f of x into g of x plus del x. Okay. Now, phi x plus del x minus phi of x is equals to f of x plus del x into g of x plus del x minus f of x, g of x, and then what we will add or subtract? This factor plus f of x into g of x plus del x minus f of x into g of x plus del x. Okay. Okay. Now, when you add and subtract both terms, we have left hand side by phi of x plus del x minus phi of x is equals to, if we take g of x plus del x as a common, we have inside f of x plus del x minus f of x, and from other two terms, if we take f of x as a common, we have g of x plus del x minus g of x. Right? Now divide both sides. The next step is the third step is divide both sides by del x. Okay. Now phi of x plus del x minus phi of x whole divided by del x is equals to g of x plus del x into f of x plus del x minus f of x whole divided by del x and plus f of x into g of x plus del x minus g of x whole divided by del x. Right? Now the last step is what? We take limit on both sides. So when we take limit delta x approaches to 0, phi of x plus delta x minus phi of x divided by delta x, and again limit delta x approaches to 0, g of x plus delta x into f of x plus delta x minus f of x divided by delta x plus f of x g of x plus delta x minus g of x whole divided by delta x. And I have applied the limit on both terms. Okay. And when I applied the limit, I will get this whole part will be equals to phi prime of x. And this part, when I will apply g of x plus 0, I will get g of x, and this is the derivative f prime of x plus this is f of x, and this is the derivative of g prime of x. So this is the proof of, or one thing more, if this phi prime of x, we will uh, this was a substituted function. So if I will write d of dx is equals to f of x into g of x. So finally we have g of x, f prime of x plus f of x, g prime of x. So this is the proof of this theorem. Now the quotient theorem is also the same thing, same procedure, same steps, and in quotient rule you will also take supposition. In quotient rule, you will also take supposition of this function phi of x is equals to f of x divided by g of x, and when you take this supposition, your rest of calculation will become very easy. And the second step, which is when in this case in our product rule, we have multiplied and divide with f of x into g of x plus x. But in this case, when after subtracting the first and second equation, you will subtract and multiply f of x into g of x, and the rest of calculations are very simple and very same with the product rule. So there is no there is no need to worry about all these theorems. These are very simple, and just you have to follow the four main steps of finding derivative of ab initio method or first principle method. So this is the end of our today's lecture, and if you have any difficulty, you can uh, you can tell me on my